you are doing what you are doing. Without knowing that, you always become bored that, okay, why I have to do these things? It's so boring, monotonous. So philosophy keeps you grounded. Okay, philosophy keeps you grounded. So I am trying to figure out where is my philosophy, where are my philosophy slides? Because after a while people get tired of my philosophy, so I stopped talking about philosophy. But you are new, so I am going to talk to you about philosophy. Okay, so what philosophy I am talking? I am talking about philosophy of a QA. Why you do QA? But let me first find where is that file. Where is that file? Let me first find out. Oh. Okay. Where are you? Here. This is here. I forgot to download it to my the computer. So it is in somewhere in a share folder. See, when you are traveling internationally, our institution doesn't give you the regular computer. They give you a computer where everything is restricted. You can't access many things. So that's it. My files. Yeah, text. It's coming now. Okay, I believe this file have all those philosophical thoughts here. I believe. Yes. These are the philosophy. These are the philosophy QA for radiation therapy. Okay. You see them? Okay. Why? What is the objective of quality assurance? All planned and systematic actions necessary to provide adequate confidence that a service or a product will satisfy given requirements for quality. Okay, so is the quality assurance is not only done in radiation therapy. You know who does very strict quality assurance? The aviation industry. You are flying a plane and you are thinking everything is very perfect. I'll go and reach my destination. But behind it, there's a strict QA procedure. And specifically the pilot, before he takes over, he goes through a long list of checklist. You know the reason that why he is so concerned about it? What is the difference between the QA we are doing and he is doing? Because he is also flying. His life is also at stake. So when you are doing QA, you think about it that your actions has certain implications on some people, your customers. Your customers are buying some products and they have to have that confidence, just like we have the confidence in flying a plane, taking a plane. Similarly, your customers should have enough confidence on what product you are offering or what service you are offering. We are offering a radiation therapy service. So they should have confidence that before they come for a treatment, that the people who are behind the scene doing all those checks and all kinds of, they're doing a great job. So I am safe. That is the philosophy, nothing much. Okay. For a radiation therapy, proton therapy QA program ensures that planned dose will be delivered within established tolerance. Delivery system built in interlocks are essential for safe and accurate delivery of a dose. QA programs should ensure that they are indeed functional and reliable. Okay, because we are not doing QA in between every field or every patient. We are doing in the morning, we are doing in the week, we are doing in a month, we are doing in a year. But between them, what happens? That the machines, those who deliver those radiation therapy, before they are used for treating patients, they they are interlocks to prevent any malfunction. Prevent any malfunction is working, and that's they protect it. So we have to check, make sure those interlocks are functional. How do you check interlocks are functional? If everything is done correctly, the interlocks are not used. So you have to somehow stress the system. Try to break it. Break in the sense that do something which will trigger the interlock and make sure that the interlock is working. This is a very big challenge. Most of the QA programs may not be designed to check those interlocks. So for young people, I challenge them. Make sure that you find some better way of doing what the older generation is doing, because older generation may not have done a superb job. There is always room for improvement. So never think that because it has been done for all these years, it's great. No, there may be something missed that may create some situation where there will be unsafe delivery. So those are the things you have to think about it. Nobody, and in practice, people always, it's called whine. You know the term whine, and they complain. Why I have to do all this QA all this time and all kinds of things? But that is the greatest mistake you do as a medical physicist, practicing medical physicist. There is always more attractive things to do, but this is something you are assuring all your customers are getting the dose that they are supposed to get. Okay, all other components, and not only that machine, there are many other things in the process of simulation to delivery. There are many processes where things can go wrong. Okay, and there is a philosophy: if you start something not very well, it's not going to end very well. If something starts very well, half of the work is done very well. So the starting point should be very good. Starting point should be very good so that things will move very smoothly, and there will be not much repetition or doing it again. If you don't have time to do it well in the first time, when you will get time to do it well in the second time? So as the philosophy is, the work is done is not the philosophy. The work is what? Well done. Okay, that is the philosophy of a QA. You have to do very well. Too much of philosophy now. Let's do some practical things. I'll stop this one because this is an old presentation. Because after a while, people, I told you already, got tired of listening to this sermon. They thought we don't need to. So I stopped telling them. Okay. Now, another thing is that's called intelligent QA. If you know the system very well, you know how to do good QA. And when if you don't know the system well, there is the problem. Okay, because you don't know what to check and all kinds of things. So it is a good idea. The physicists have to have a better idea about what their system is and all kinds of things. But nowadays, with all automation and black box programming, it becomes very difficult. It is a challenge. It is a challenge to know everything. Okay, so you have to gather a team. The and the team individually you may not have knowledge, but the team has the knowledge, and the team should be willing to share and the responsibility. It's not a one individual's responsibility, it's a team's responsibility, it's a teamwork. I consider a physics team as a soccer team or a cricket team or whatever sports team. Not everybody in the team is capable of doing the best in all areas, but they have some strengths, and together the team wins. Okay, so that's what happens. You have to have a great team, and you know what an orchestra is. In an orchestra, you you play music. You play music. There are many things. Many instruments. Many players. They are playing their music individually. But eventually, you have a great music coming out if everybody follows the direction, and suddenly somebody starts making noise out of the tune. Then you don't hear music. What you hear noise. Okay, so you have to create a team that is playing in such a way the orchestra, the music coming out very well. Okay, so that's all. Teamwork is the key. But unfortunately, there are situations where you are alone. That I always avoid to practice that's which is only a single one man show. It's not it's radiation oncology is not that way. If you are a single person working somewhere, you should have access to another person with whom you can discuss things. Okay, now, there are many things when there are many things we don't know, but there are other people who know those things. You should have that open mind, that that thinking that it's not possible for me to know everything, but I have an open mind. I'll approach another person and tell them, hey, I don't know this, can you help me with this one? Okay. Hmm. This is what I wanted to present to you, is coming up. I'll skip a lot of slides because they're not maybe relevant. I didn't find time to delete them. How many people have participated in some kind of a QA work in radiation therapy? Only one? Two? What? You work in the clinic or you have observed with somebody else? You do daily QA. Yeah, and you do patient specific field measurement. Hmm? Hmm? Yeah, yeah, yeah. Very nice. So you know something about it. Okay. Okay. Hmm. That's good. So you like it, or if you like it, what you are doing? Do you like it? What you doing? What are you doing? Do you enjoy it? What you are doing? That's very nice. You will be great physicist. You will be great physicist. If you like your QA method, then that's wonderful stuff. Okay. Now let's start. Okay. So before you do the QA, as I mentioned, you have to know your system very well. And in our business, there is an accelerator and beam position, energy, current, steering, and a extracted beam quality. And then the beam transport, beam positioning and profile. This part is part of engineering and maintenance QA program. Okay, we leave it them to the engineers. We have every day after the patients are treated, they take over and they go through their QA program. They have a QA program that they have formed, they fill up, and then they release it for physics QA. In my old days when I used to travel in a train, when the train reaches a big junction, people will come and start hitting the wheels. Okay, just to making sure that okay, nothing is loose and all kinds of things. So that is QA. Okay, that's QA. That's QA. So, so treatment nozzle, where the beam shaping and monitoring device, dose monitoring, gantry, couch, positioning, imaging system. This is part of a physics QA program. Whatever comes out goes to the patient treatment, and whatever used for putting the patient, imaging the patient, all kinds of things, that's part of a physics QA program. And these QA checks are performed periodically. Some QAs are done daily, some are monthly, some are annual. Why? How you decide what frequency you want to do the QA? The daily QA, the daily QA, wow, the daily QA. So where do I put it? Okay. The daily QA is very important because the machine was down for machine was in a standby for some time, not used it, or some power might have gone out, and after the preventive maintenance done by the engineers, they gave the machine to you for clinical use. So the daily QA, you have a good snapshot of what how you treat the patient. That same thing that you do the patient, you try to mimic as if you are treating a patient, and everything is coming out good. Basically, the dose output is good and the imaging system is working the way it is supposed. And most important thing, all the components are communicating with each other, because you don't have to, if you face a situation, the patient you put in the table, therapist put in the table, and suddenly they see their images are not being transferred, all kinds of things. There is no guarantee that it will not happen. It will not happen, but at least you feel good that you have done whatever check necessary. When you are doing the check, everything was working okay. All right. And the frequency of these QA tests are decided based on the severity of failure of whatever you are checking. If the severity of failure is not that high and the system doesn't change that, not supposed to change that quickly, then this is taken into as a monthly QA. Annual QA is to make sure the way you configure the beam in your treatment planning system, the dosimetry parameter, the dosimetry data, they have not been changed over the time. Okay. Of course, 1 year is too late, too long to wait to do that. That's why the periodically we check patient treatment field dose distribution. If that is working, then at least you have confidence that nothing significant has happened. So, and specifically, with IMRT and all kinds of things, every patient's treatment field is separate, different. So that kind of the patient treatment field QA helps you to make sure that whatever you plan is going to be delivered. Okay, so that's why that's done every before starting of every patient. That's what the annual QA is, to again repeat all your commissioning, some subset of your commissioning data to give you confidence that the machine characteristics have not been changed. So that's what the annual QA is. So this is the delivery system. Qualities need to be assured. This is for passive scattering beam, but this is applicable to all kinds of proton therapy. Dose monitor calibration, that has to be done. That has to be checked every day, and that has to be done every monthly by a physicist. The daily monitor calibration or daily QA check, daily dose check is not done by physicist. Basically, it is done by therapist or done by another person, physician assistants, with a system that is independent of what a physicist uses. So just it's a constancy check. I'll discuss more details about it. Relativity output factors and dosimetry parameters that you use in calculating the monitor units or doing your the absolute dose calculation for the treatment fields. A range of different RMWs or options or different energies that is being used for treatment. Radiation field flatness and symmetry for spot scanning beam. It is the spot profile that you check. Gantry and couch rotation isocentricity. The gantry and couch are movable objects, and your radiation isocenter should match with the mechanical isocenter in which you are moving the patient. Okay, and the imaging or the imaging of the patient before it comes for treatment is done by X-ray system, but the treatment is done by the proton machine. So they are not same. But you are telling that a patient, my target is my isocenter of the isocenter inside the patient is located here. By X-ray you check it, but you are delivering proton beam. What is the guarantee that a proton and X-ray isocenters are matching? They have to be checked, making sure that the X-ray system and the radiation center, they are matching properly. Okay, within a certain tolerance. We take those uncertainties into account in our robust optimization. Cause translation, patient imaging system functionality, safety interlock functionality, patient treatment field dose distribution accuracy. Those are the things, those are the parts, those are the checks that we do as a part of our quality assurance program. Daily machine QA ensures that the dosimetry quality of the proton therapy is acceptable. The different communication of different computer systems associated with the treatment is function properly. The imaging and the patient position systems are functioning properly. All the critical safety interlocks are functional. Okay, because what happened is if for some reason the beam pause button is not working, and suddenly patient has some issue that you have to stop the beam, you cannot stop the beam. Beam pause, beam abort, radiation warning sign. Somebody, you are treating some patient and somebody is trying to get inside the room by mistake. He or she is not going to be exposed. So that kind of a door interlock. And also when you deliver the treatment, you are monitoring the patient by camera system. That camera system should be functioning okay. And then you communicate with the patient with some intercom system. That intercom system should work. All those are safety features. There are many things that you need to check that they are working. So how do you decide what you want to do? If that there are some professional organizations who give some guidelines that these are the minimal things you have to do. You have to assure that everybody is doing those minimal things. So one of the recommending body in USA is called AAPM, American Association of Medical Physicists, and they have a report that's called Task Group 224. I am supposed to discuss that as part of this program. So this is what their recommendation is. If you look at ICRU 78 report, they have also a quality assurance program there. That is applicable not to that is a international QA guideline. So you can look at it if you get a chance. So these are the things. There are some dosimetry, as I have already talked about it, and they give you the tolerance. Okay, that what tolerance you should maintain. Mechanical imaging, cone beam CT, all those things has to be done in Delhi. I'm not going to one by one to go through it, but I am just giving you that this is a reference source. It's called AAPM, American Association of Physicists in Medicine, Task Group 224 report. Okay, and it is published, and you can upload from AAPM website also. Okay, so that's why I encourage those of you who are going to medical physics, for sure you are in a program, a training program, just become a member, student member, or become a member of associate member, and then you have a lot of resources available to you about this QA and standards of practice, practice guidelines, all kinds of things. There's a lot of resources are there. Okay, so these are the safety checks I was talking about. All these things I've already talked of. There are some optional things that you may do, you may not do it, all kinds of things. So those are the recommendations. Okay, here are some devices from our center that we use. This is a cube. This cube is a variant cube that is also used in true beam. First thing is you have already you know that where is your isocenter, mechanical isocenter from the laser position. So you have a cube, there are some marks, very simple test, and you have determined where to put this one to make sure this laser will match with the crosshair here. So that coordinate of the couch is already determined. So you put that jig there, move the couch early in the morning, and make sure that laser is shining there. So that way you know that the lasers that are used to position the patient at the isocenter is correctly functioning. Okay. So another thing that you cannot, in the morning you don't have a luxury to take your time to finish the QA, because you have only certain specific limited time to finish your QA, because the patients are waiting for treatment. So you cannot take long. So that's why it is the responsibility of the physicist to create a robust and fast QA program for the morning. Okay, and train the people who are doing to do it very well, very quick. So that is one of the goal of the that is one of the responsibility of the physicist. So then this happens. Then what happened? You take an image of that cube. In the image of the cube, in the imaging system, you see a BB there. Okay, you see a BB there. And if the BB and this crosshair are matching, then your imaging system isocenter is matching with the mechanical isocenter. Okay, because you have already verified your BB is at the mechanical isocenter with the laser already. And then you take this one, and this ensures, okay, that where is the laser, where the laser is, where the cube is, there is the imaging isocenter. The imaging isocenter is there. Okay, this is one projection. You can take two projections. One is a lateral projection, one is epi projection. So you know x, y, z coordinate of your of this BB. So once you have an imaging isocenter and you know that laser is matching here, then you position your dosimetric device, the ion chamber, in that laser position. Okay, and you deliver the dose. You deliver the dose, and then check that okay, the dose on some specific conditions are passing the tolerance. Okay, so this is already decided which day what, because in the proton machine the problem is there are many options. There are many options. You cannot check them, all of them every day. In a standard Linac X-ray machine, they have two X-ray beams and six or seven electron beams, nine options. So you can probably check all of them. But here, there are so many options that you cannot check them. So that's why you periodically check them every day. Check some sample options, and then at the end of the week you might have done a subset of enough sampling that everything is working okay. All right, then what comes next? Then comes monthly QA. I have given you what the daily QA is. So we give them a form to fill up. Not only the dosimetry form, this form is not complete. There are many other parts that in proton therapy, the range verification is very important. The beam energy verification is very important. So what happened is you have some material, put it here, then you will be measuring at the center of the SOBP or center at the center location. Then you take out some material, then it will give you a position where you can measure the proximal part of it, add more material here, phantom material. So in this way, you are measuring the distal part of the SOBP. So there are three sets of measurement done: one at the center, one proximal, and one distal. And there are baselines being determined that what reading you are supposed to get, and the reading daily measurement reading is compared with that, and there is a tolerance. And if the tolerance is met, then it will say pass, pass, pass. Okay, and then and there is also a safety check list there. Okay, the people who are doing the daily QA, they have to mark them. They have checked all of them. Okay, the physicist would have enough confidence or a trust, not confidence, the trust on the people who are doing that they are doing those things. Okay, sometimes they may be in a situation that they may not finish it, but we have instructed them, no worries if you cannot do it. A physicist is always available to come and help you. So we give them all our phone number, no matter what time in the night. This is the calling tree. You call one by one, see if any one of them is available to help you. Okay, don't see something wrong and just leave. Don't ever do that. Just call us. We will come and fix it and then take care of it. Okay. You see, imagine when the Proton Center opened, I'm giving some break from listening to the monotonous QA things. When Proton Center opened, we didn't have physics assistants. The therapist didn't have enough knowledge to do the QA. So we used to come at 5 o'clock in the morning and do the QA. We did it for about a year. And then we thought that we were losing too much of a sleep. So, so then we pleaded with our administration, give us some physics assistants. And it is very difficult to find dedicated physics assistants who will do day after day, month after year after coming early in the morning at 4 o'clock or 5 o'clock to do this measurement. So that's the difficult thing, find trustworthy and people who don't get tired with this one. But somehow they have stuck with us for many years. That means that we give them, they come in the morning. We do not expect them to work too long. Okay, just work for a couple of hours, then they leave. And after that, what they are doing, we don't ask them. Okay, so they enjoy. So that's why they don't want to leave. They help us, so we try to make their life a little more enjoyable. So that's how it works. And most of the places, if you have graduate students, those who are doing PhD or doing some project, they are also sometimes help with this one. Okay, they are there for a couple of years. They do this, then another group comes in and they help with that one. So if you have a good training program or educational program, those people are good fit into doing this kind of things. They learn and they help you. Okay, so that's monthly QA. These are some of the tasks you do monthly. What is the okay, this is for passive scattering, compensator placement accuracy, imaging and treatment coordinator, incidence accuracy, proton and X-ray field. As I mentioned that you are imaging with X-rays but treating with protons. So if you have using some apertures, the aperture imaging should match with what you plan. So those kinds of things are being tested. Safety, all delivery system safety is functional. That's done by this monthly QA is done by physicist. The monthly QA is done by physicist, so a little bit more comprehensive. And if you have imaging, you have all imaging system. If you have a cone beam CT or a CT on a rail, 3D imaging system, they have to be checked also. They're functioning well. So these are the list of a monthly laser versus X-ray imaging system, radiation field dose, all distal SOBP width, flatness symmetry, range uniformity check, output versus gantry angle check, gantry angle accuracy and mechanical isocentric check, table translation and rotational motion accuracy check, mechanical isocentric check, snout horizontal position accuracy check, patient positioning system accuracy, X-ray and proton field coincidence check. There are a long list of checks that a physicist does every month. Okay, let's move on. These are some of the devices that is used for monthly QA. You put a chamber here, so this can rotate around and you can measure the gantry out, the beam output at different angles. Okay, so this is some way to make life easier. And these are the beam flatness check symmetry. You can use a dose array, ion chamber array to do the flatness and the symmetry check. And these are some very simple devices to make sure that check the mechanical isocenter of the beam and imaging isocenter. And this is some special test that you do, that the beam uniformity is maintained at the distal edge. Okay, the distal edge beam is still uniform. You cannot check that uniformity if you do this check at the center of the SOBP. So in order to check the beam uniformity, you have to do at a distal part of the Bragg peak. So what happened? A small 1 millimeter thickness difference will make the profile look completely different. So from there, you can distinguish. You can find out if how uniform is your beam. Okay. This is the annual QA. The TG24 tells you what are the annual QAs you have to do. There's a lot of things that needs to be checked, and they give you the tolerance, and you follow them, and this is a minimum requirement, and this is not any machine specific. Your machine may be completely different than another place that at another facility. So you have to make sure that your QA program is tailored to your specific machine. Okay, I am not expecting you to remember all this because this is published. You can look at it later on. There's a long list of tests that you have to do, mechanical imaging, all kinds of things that has to be done. So this is a summary of what I showed you in that report. Standard calibration. You will do in the afternoon how to do a TRS 398 calibration. I want all of you to do and make sure you are ready to do the beam calibration. Okay, that is a task nobody can do. Only a qualified medical physicist can do. Okay, nobody can do for you. You have to do. You have to sign it. Okay, so the regulatory bodies look for it. That when they come to inspect the facility, they'll look at they don't look at many things, but they will ask, where is your beam calibration report and who did it? Okay, that's that. And it has to be done once in a year, and it should not, you never make a delay in finishing your dose monitor calibration. Okay, then who controls, who inspects the QA program in India? Yes, okay. So that's good. You know already. So they are very strict. They will fine your facility if you are not doing the whatever you are supposed to do. So we are always afraid of them. Okay. So we have to make sure that you do all this good work. Then suddenly you forget, hey, my annual Q was due, and it's already passed, and that is a nightmare, and and you are in trouble. So all of us put in your calendar 1 month before that it's due, to remind us, hey, annual QA is due, so go and do it. Okay, so these are some, as I mentioned earlier, your yeah, your annual QA reconfirms your beam characteristic has not changed. So you have to do all the things that you do for commissioning, not all of the things, many of the things that you do for commissioning to do spot check of your beam dosimetry parameter, like the IDD for spot scanning beam, spot profile, all kinds of things that you have to do, annual calibration of dose, and whatever you need for your treatment planning to check your treatment planning system. There is also a treatment planning system QA. There is also a treatment planning system QA because it's a computer, and nowadays viruses are all around, and specifically in India, there are viruses are easily available. And we are not allowed to use these USB ports in any computer. You put it there, then you get a virus, and our institution has disabled the USB ports in all computers. That you cannot bring a USB from somewhere and put it there. That's not allowed. It has to be new and has to be tested. And you have to have administrative privilege to put your USB there. So the hospital environment, if the computer system gets infected or has a cyber attack, it's a disaster because we depend on computer so much. Our treatment machines without computer they will not function. Okay, the Hitachi system, computer system, is not connected to any internet. They will never allow to. They never allow it because they are very afraid that sometimes they happen. The whole treatment control system will come to standstill. Okay, you can't treat. So you have to be very careful. Nowadays, the cyber attacks are so frequent, and there are smart. These guys are very smart. They want to make your life very difficult. Not only steal your money, but disrupt. They disrupt the whole the life in an enemy society and things like that. Okay, so you have to be very careful about that. Yes.
These companies like Varian, they ask for online remote access to the.
Yeah, but you know the person. You have to know the person. You have to know the person who is asking. That no, it's a very nowadays. What happened? You don't trust who is calling you. You have to have some way of verifying who is that person. When I get a call from some unknown thing saying that okay, I am calling from this, I said, how do I know you are calling? I'll call you back because you have the number given to you very young that who is your service representative. And if you know your service representative very well, you know his voice or somehow you have to verify. Trust but verify. Because don't give the access computer to an unknown person, okay? That is a that in this generation, in this time, that is the most common sense. That common sense has to be developed in everybody, whoever is using computer system, not to allow anybody to have access to your computer without knowing who is the person. Okay, that is the first precaution you can take. Sometimes we are in a hurry. Somebody calls and makes you to feel that okay, you have to take care because you don't have time to verify, and that's when disaster strikes. Okay, the disaster strikes. Disaster strikes at that time. Okay, people have lost money. People have lost all kinds of things. Okay, avoid disaster by all means. Okay, whenever possible. Beam data constancy check, relative output factor, all kind of daily. So what happened is you have a daily QA baseline that your physician assistant or therapists are using. So as a part of annual QA, you check it that baseline is good. So that's what is done. We have already discussed annual TRS 398 calibrate based protocol. Let's move. These are some of the tests that you do also, cows gantry, X-ray system, delivery system, safety checks, all those things are part of annual QA. These are some annual QA tools. These are I showed you the multi-layer ion chamber that you can use it to do a quick depth rose curve. These are the devices to check your radiation isocenter, mechanical isocenter, and these are all devices to check the mechanical isocenter, the water tank to do your scan. the matrix array, ion chamber array to do profile measurements, all kinds of devices that you have at your disposal to make your life easy. So this is the spot scanning beam. Lot of things are same. So only thing you have to make sure that you have to range of individual spots, spot depth dose, spot profiles, spot positioning. Those are the important things in doing QA for proton pencil beam, scanning proton pencil beam. So there are many devices you can use because in this case the field is not broad. The field is a single, you have a single spots, but you can create a broad field also. But how do you, as I mentioned, we have 94 energy selections. How do you check that? You for cyclotron, where you have only one energy, but this you can change the range of the beam by putting that energy degrader. The checks may be little less, but for synchrotron system, the checks are many because of there are multiple energy layers that are being used for treatment. So some of the things is you have to do the proximal, center and distal point doses measured every day, and then of course do the spot positioning accuracy check. That's very important for daily delivery of the dose. And then of course you have to do the dose for monitor units. Monthly, same thing done by physicist, and they do the mechanical and imaging system checks. Annual, this calibration, and also the dosimetric parameters of the spots. So that you have to check. What is the difference between what I was talking before and what I am talking now? That was I was talking about passive scattering beam. I just quickly went through it. And now this is what is more important because most of the facilities have a proton pencil beam. So these are the QA that you should pay more attention to it, okay, if you want to work at a proton therapy center. So in daily QA, you can have different devices, but a multi ion chamber device is very helpful. There's a device available, many devices are available commercially that you can do daily QA device from IBA, multi-ion chamber devices from many from PTW, all kinds of things are available. So you can get one of them and design your QA program to make use of, because you have at one delivery, you can deliver to different locations, okay? So that saves time. You can of course use a matrix that which has about 10,000 1080 ion chambers to use it, but that's a very expensive equipment. You don't want to the physician assistant therapist to handle it and break it, all kinds of things. So you have only one or two of them. So there are, you for daily QA you find a device which is which can be replaced easily, because the possibility of those systems being damaged is very high because they're doing in a hurry early in the morning and all kinds of things. So that's why you have to buy some device which can be easily replaced and will not cost that much. So that's why this is a cheap, this is a relatively cheaper ion chamber, multi-ion chamber device. And there are many other better are also available. So when we are trying to develop our QA program, this is the thing available in the department, so we started to use. This is just an example. Don't think that this is what you have to look for if you are doing your QA. What you look for is a multi-ion chamber device, so that at one shot you can deliver different beams at different locations. All right. So you can deliver, in this case, we can deliver 5 spots at the same energy to program at a different 5 chamber to position the spot at 5 locations. So in this case, you have a baseline reading and you read it. So if its reading is matching, then you know the spots is going to that location. So you have a verification of a spot going to that same location. And then when you deliver the spot through a electronic medical record computer, it also keeps a log of that where the spots are being delivered. So another thing you can do is you can go and look at the log file and see that what position the spots were delivered. But this is a redundancy check. You are independently checking if the spots are going to wherever you're supposed to go. The spots positioning check can also be done by a film. You put a film there and you put those spots at a known position and see if the spots are showing at those positions also. Okay. So, but in this case, what happened is we wanted to do many things using the same device so that you don't have to change from one to other. So this multi-chamber device helps you to fast to check the spot position. Okay, after that is done, then what you want to do is you wanted to do the range check, SOBP, the PDD check. That means you want to take a couple of points and make sure that the depth dose curve is good, looking good. So how we have programmed three energies of a different energy. So what we can do is look at this depth dose curve for three different energy spots. One is high energy, one is medium energy, one is low energy. And you put certain amount of phantom material in the path of the beam here. Some phantom material is put it here. This is the device, dose measuring device is sitting there. This is a jig which has a multi-purpose. First thing that you can put the cube here, then you can place for here to put your ion chamber, and then you add different phantom materials to change the depth where the chamber is being irradiated. Okay, so in this case, in one shot, I'm just showing you the philosophy, what is the, how you can with the least effort get maximum information, okay, in a QA, in daily QA. So this depth corresponds to the Bragg peak depth of the peak depth of this medium energy. And this is the proximal part of the high energy beam. So you measuring the proximal dose, you are measuring the peak dose for this energy, and this depth is the distal practical range of this beam, low energy beam. So at one shot, you are measuring the dose at a peak, dose at a proximal point, and a dose at the distal part. So if you have, this chamber has only 5 of them, okay, we are using 3 beams, but you have suppose a device which has a 10 chambers. So you can also do 10 energies at the same time, okay. So at that time, we didn't have those devices are not available. In our new center, we have bought that device, 4 of them. Every room has one of them. So they are not that expensive. So they can be, many energies can be checked. Okay. Did you get the idea that what the objective is? Objective is that as quickly as possible, you want to check as many energies as possible. Okay. So then the readings for all these test beams have been determined before by physicists to give the baseline, and the readings at those locations are compared with the baseline. From that baseline, if the deviation is more than tolerance, then it fails. If it is within tolerance, then it passes, and then you verify the depth dose curves are good for these energies. You are not, that doesn't guarantee that other energies are okay, but the the Hitachi machine or whatever the machine, they have interlocks to making sure the energy of the beam is not changing. You are just doing a redundancy check, making sure that okay, whatever they are seeing, you are also seeing that one. You are also verifying them by actual measurement. So then you have to check the output, beam output. So this is done a volumetric broad field. Do you understand what is a volumetric broad field? The beam that comes out of accelerator in proton pencil beam scanning beam is a pencil, very narrow beam, in single spot, okay? You can combine those spots to create a broad field, treatment field. If you have not understood this much, then this is that probably you didn't get much of what I was talking. The reason is, in proton pencil beam, I gave you an example that is like a painting something with a paintbrush. You have a narrow pencil beam, you have a scanning magnet, and that pencil beam can move around and deposit the dose, and together they give a broad field. Broad field means that the size is not very small like a pencil beam. It's a broad field, can be any size you decide. You want a 2 by 2 field, 3 by 3 field, any irregular field for patients. That is happening how? Because you are putting spots at a different location at a different depths, and so that you are irradiating a volume with the dose that you want. That is called a broad volumetric field. Understood? Okay. You have a pencil beam that you are using to create a volumetric dose distribution. Okay. Did you understand what I am talking? No, you want me to tell you again? You seem to be, is it clear what I am talking? Hmm? It's okay. I wish I could go back and show you something. Yesterday, we spent a lot of time showing you the patient treatment fields. The patient treatment fields are not narrow pencil beams. Patient treatment fields are broad, okay, wide, broad, irregular, and it can go to different depths. Okay, those are the broad volumetric fields. Those broad volumetric fields are used for patient treatment and so you have to check not the dose output from a spot beam, but also for a broad beam also. For checking that broad beam, what happens is this is what is done as a part of our daily QA. So we have created a daily QA broad beam, and this is stored. So the people who are doing that measurement, what they do is you have this device. Into this device, they deliver that broad field, and these chambers will read something, and those chambers readings are recorded. Okay, so that's what is called dose per mu constancy check. So these are the things that they read and they write it down, and then if they pass, then we check different beams on different days. There is a high energy broad beam, this is a low energy broad beam, this is the medium energy, this is the lowest energy. So these three things are repeated on different days, and so that you check all of them once in a week and make sure that they pass. So these are some of the mechanical checks that are done: laser X-ray system imaging, alignment, gantry angle accuracy, mechanical isocentric checks, table translational rotational, and mechanical isocentric snout. Yesterday somebody asked me snout, that snout that is moving. So you make sure that snout movement, whatever you are programming, is going to the same position. The couch is going wherever it is programmed to go, and is rotating wherever it is correctly. And X-ray and proton field coincidence check, output versus gantry angle consistency. These are part of a monthly checks done by a physicist. So couch rotation check. How do you do couch rotation check? We put a cube here and do a imaging of that cube at a couch at 0 degree, and then rotate it and repeat that imaging at two different angles. Okay, so if you see that the cube center is at the center of the imaging system and is not changing when the couch is moving from one position to another position, then you ensure that okay, the couch the couch isocentricity is maintained within that tolerance. This is one of the simplest checks you do. You put a ruler on the couch and move the couch to certain distance and make sure that you agree with this one. This is one of the most simple or simplest checks that we do with the couch, but it is simple, but it is necessary because you are relying the automatic shift that you apply is couch is moving there. Okay, so you have to make sure that calibration of the couch movement is correct. You do both X, Y, Z direction and make sure they're all good, and snout position. And this is the coincidence of proton and X-ray field coincidence. So you have a cube here. You take the X-ray, and under it there is a film. There's a film. You can do it from either this angle, or if you are doing from lateral angle, you have a cube. You have a film here. And when you do the X-ray, you will see the image of the cube in this film, and then you irradiate it with a proton beam. Then you will see that that image of the radiation field there. This is what it will look. You have the cube, and this is the radiation field. And this cube center is verified to be at the center of the X-ray system. Okay, and this is the radiation field. You scan it and make sure that the center is here. Okay, so that's how you check the radiation field and X-ray field coincidence. What is this one? Output consistency check. You do the output check at different angles and make sure they are consistent. You can do another way. If you put an ion chamber and do it, it is sometimes not possible to do it at all angles. It takes a long time. If you want to, if you want to do at many angles, you can put a device into the snout and rotate it, and it will read it at different angles. Okay, this is very important thing, spot positioning accuracy check. So what happened, you have a scintillator plate here and deliver some pre-programmed spots, then it will give you, there's a software that will give you the spot position, not only the spot position, it will also give you the spot size. What is the size of the each spot. So and do the analysis, and then it will give you some average value, all kinds of things, individual spot size, individual spot position and spot size, and you say make sure that they are and under tolerance. Okay, we should stop in 5 minutes. Let's see. Mechanical, all kinds of things that you do, gantry, isocentric, logos. There's a system available which helps you to do these quick checks. So you use them and check them, and make sure the gantry isocentric, isocentric are maintained within 2 millimeters. I've already. Okay, X-ray imaging system. You take a phantom and do the X-ray imaging of this phantom. You have a reference image compared with that one. Make sure that the positioning accuracy is maintained. So you can move this phantom and check another image. You know how much you moved, and make sure that your imaging aligning system is predicting that it is moving the same distance. Okay. You have different alignment mode. Make sure this all alignment mode that is accurate, is accurately predicting whatever shift you are applying. This is the logo system, and this can give you very quickly and the coincidence, the deviation or misalignment of the imaging and radiation isocenter, radiation isocenter. So this has some BBG inside it. From the BBG, it decides where are the imaging isocenter, and this has some the surface is painted with this is a scintillator. This cone is a scintillator, has a scintillating materials on it. So when the radiation goes through different parts, from different direction, it knows that where the radiation is coming from, and it can reconstruct where the source, what is the isocenter of that beam, isocenter of your of those all the spots delivered from different angles, and then you can compare it with the X-ray system isocenter, and then calculate what is the deviation, and that gives you a quantitative measure of the deviation, and if it is within tolerance, it passes. If not, you have to do more investigation. Okay. Monthly imaging QA quality check. So you have something called, there are phantoms available called CAT phantom, and then you can take your cone beam CT, do a cone beam CT of this phantom, and try to analyze the image quality based on this kind of visibility of some of the material inside it. So there are tolerance limits that how many of them you should be able to see and identify. Based on that, you have the image quality, KV quality check, and phantom that then you have some material here, the line, how much lines you can read. Based on that, you can decide that if the line, how the contrast, if the image contrast is good for your purpose or not. All kinds of things can be done here using some of the devices. And a KV quality check in the sense that the KV you are setting in your imaging system is correct. That's giving the correct, giving the good quality image also. Okay. So every year you check the depth rose curve depth dose curve of selected energies that you have acquired during the annual commissioning, and make sure that they are agreeing within certain tolerance. Okay, that you used to do with a water tank, but now with the availability of the giraffe, we stopped doing water tank. It's easy to get large number of curves like this using that giraffe system. Do you remember giraffe system? I'll show you. Yeah, here is this one. This is the zebra, and this is the giraffe. What is inside the giraffe? There is a very large chamber inside the giraffe. Many of them at different locations, and they measure what? Remember IDD, integral depth dose of a spot profile. Everything is being measured. We discussed at length yesterday what is IDD. I hope you will remember what is IDD. Okay. Then you have this Phoenix, which can measure the spot profiles very well. So those are things are helping us to do very quick checks every year, the depth dose curve as well as the spot profile, that can be very easily measured and compared with the commissioning data. Okay, these are some of the tools you have already seen. Where I am. Okay, these are depth dose curves. Then you have to do the spot profile analysis. Then, of course, you have to do the spot positioning check. You can do it many ways. I'm just giving you an example how you can check the spot positioning with a film. You have already created a spot pattern at a known separation at a known positions. Irradiate the film. It can be, you can easily measure from center to center what is the distance, or you can scan this one, and that will give you that what is the center to center look, all kinds of things. You can write a software, use any film scanning software to analyze your film. So that's why, because it requires some additional work and it is not online, you don't get the results immediately. You have to spend time in doing the scanning and measuring. So that's why we have moved into these devices, these kind of the scintillator devices, that they can give you very quick result. I'll show you another device. Probably I'll show you again, just to remember how live. Okay, this device, very simple device. You irradiate it with known spots at known locations. Then from the radiation, it can give you where the spots went and what is the spot profile and the spot size is also. The film was used before these devices became available. Why these devices were not available before and why they became available now? Can you think of a reason? Because these devices, to produce them, cost money, a lot of money. And no company is going to make one for one center only. But now there are many proton centers, so they see a business. So that's why they produce it. Before they didn't see any business with one or two or three centers. So that's why those things were not available when we started our proton program. So but now these are things available and making life easier and checks much more accurate and to do your quality assurance checks. Okay, these are the list of things that we do annual machine QA, and this is something that you do for passive scattering beam. That if you are using aperture and a compensator for a particular patient, every one of them has to be QA'd, just to make sure that they're manufactured or fabricated properly. Okay, so this is part of a patient QA now, and this is a, you want to make sure that the dose that you are supposed to deliver is delivered correctly. So you have to check your monitor units for passive beam. I mentioned something about those factors, and from there you can calculate your MU, and you can measure it and check it. And you can take also the planar dose. You can do also planar dose checks also. This is part of patient QA, and this is something what we do with passive scattering beam MU calculation. I can show you an example, and it will ask you to do a calculation so that you know what goes on in the afternoon during the tutorial. Patient specific QA. When we started treating patients, we started with the prostate patients, easy, two fields. So we wanted to develop some QA to check those fields. So somebody came up with this idea, let's buy a fish tank, because the shape of this phantom is looking like a prostate, okay? So then we did a CT scan, and with this CT scan, you can always do a verification plan with this phantom, and we'll find what dose is there at the center. Then in the chamber, you put it there and measure it. So that will verify the dose from the spot beam that you are delivering there, and how accurate is your treatment planning system prediction. And of course, then we have to do planar dose. So we have a large matrix array here, a lot of ionization chambers. And then you put the phantom and irradiate the field, and you can get the dose. You can get the 2D dose distribution also. I don't have prostate field, but this is a dose at different points that are measured in a SOBP. This is a right lateral field, this is a left lateral field. In the beginning, we did a large number of patient point measurements, because we are learning at that time that how to verify those doses in for those patient treatment fields. So gradually, we became a little bit more confident that okay, our system is working well. So instead of doing 10 measurements, we are only doing one measurement. Okay, because that's how and in order to reduce the number of measurements, we have something else that is used to check the treatment planning system. That we have an independent dose calculation system. We take the spot pattern and put it into that system, and that system generates the dose also, and that is compare. I'll show you. Okay, that's a Monte Carlo based system. So it calculates the dose for the treatment field, and we compare with the measurement at one point, and also compare with the treatment planning prediction. So that way the QA is done by independent calculation. So that may allowed us to reduce this number of measurements. Okay, makes sense what I'm talking about? In the beginning, when we didn't have many things, we didn't have an independent dose calculation engine, all kinds of things. So we try to verify the dose doing multiple measurements at multiple depths. But gradually, as we started gain experience, and also we found out that what else we can do to reduce this measurement time. Then something came, okay, let's develop an independent dose calculation engine. Then once that is developed, that gave us confidence that the treatment planning system dose can be verified that way. But both the system has to be checked. So we do one measurement, make sure that both of them are giving correct, the measured dose is matching with that point in both systems. And then use the independent dose calculation to verify your treatment planning dose distribution. So you see this is a very irregular field, and we are measured the dose in all these locations. They agreed well. And okay, this is the profile that we measure and compare with the treatment planning system. And these are some of the examples how the QA is done. This is what I was talking here. This is a independent, this is a H plus QA. S stands for Proton. This is the independent dose calculation engine. So you have a depth dose curve from the treatment planning system, that is a red line, and then you have the depth dose curve from the independent dose calculation, and these are the measurements, and you compare it. They're agreeing that they should agree very well within certain tolerance. Okay, this is also another example of how we verify the patient treatment field dose. And then we become more ambitious. And what we do is that every time a treatment field from the spot scanning beam is delivered, the system keeps a log of where the spots are going. Okay, both the Hitachi system keeps it, and also our record and verify system keeps that log where the spots are delivered. So we developed a software to extract those spot position and compare with the planned spot position. There is always some deviation. There is always some deviation because the magnetic field, that the scanning magnet may not be as a tolerance, how accurately it can place the spots. So, but there is a tolerance. Within that tolerance, we analyze them. Then we have a plot. We plot it. Okay, how they are looking for, what are the what is the mean distance they make, how far they are deviating, from the planned position, and we try to quantify them. What is the average distance? All kinds of things, and make sure that they are within 1 millimeter. Okay. You have time? Let me finish this one. Okay, you can take a break. We can start after half an hour when we take the break. Okay, let me finish the QA part. Then we'll do other part. Another thing is, another aspect of a QA program is the check of the treatment plan. The treatment plan is created by a dosimetrist, and it's checked by a physicist. Okay, the physicist has to look through the plan, the dose distribution, everything, and then sign it. Then only the patient will be treated. So it is the responsibility of the physicist to make sure that the plan is created without any mistake. No mistake is done at different stages of planning. Okay, the planning process goes through has many steps. You have simulation, you have image, the correct image is used. Then a correct treatment field parameters are chosen, because what is the spot spacing, or what what are the objectives of optimization, are they properly done or not. Okay, so those are the responsibility of the physicist. Before the plan is used for treatment, then we have to go through a list of things that a physicist checks. Okay, so that's I mentioned already: correct patient image, correct CT scanner, the immobilization of the patient positions are appropriate for the treatment site. If the patient is not properly immobilized with a proper device, then day-to-day setup is not reproducible. So that's the most important thing. You want to make sure that that is correctly done. Patient orientation and treatment sites are correct. That is a disaster. If for some reason the plan is done to a location where physician is asking for somewhere else, physicians do make mistake also, because they sometimes forget that what location the target is, and all kinds of things. So, and targets are drawn incorrectly, all kinds of things. So physicists cannot always detect that, but they look at the planning directive and make sure that whatever is written in the planning directive is matching with whatever the plan is done. Sometimes it's possible to verify that the CTV is done, CTV is greater than PTV, or CTV is greater, GTV is outside the CTV. All kinds of things you find, then you bring it to the attention of the physician. Okay, to err is human. To err is human. To admit, you have to have courage to admit that I made a mistake, and you have the courage to, or you have the attitude to rectify the mistake. Okay, and that happens very much in radiation oncology. That's a very error prone. I say radiation oncology is a high-tech medicine, and high-tech medicine is very error prone. So you have to have always that mindset. Some mistake might have happened. Okay. All the relevant critical organs are contoured. Okay. All organs with possible change of shape, density are identified. IG material and artifacts are identified. Uncertain CT numbers and any relevant regions of interest are appropriately changed, ensuring the target coverage and safe dose to the organs at risk. Correct target volume is used for planning. Calculation options and dose calculation grids are correct. Beam orientations are appropriate to meet the plan objective. Okay, those are some of the things that you, as a part of a plan review. Anything else? There's more. Isocenter is correctly entered all beams and set of fields, because sometimes your treatment field isocenter has some coordinates. They should be always matching with the set of DRR that the treatment planning system is generating. What the set of DRRs are doing, that's called digitally reconstructed radiographs. Those digitally reconstructed radiographs are used as a reference to set up the patient. So you have planar radiographs reconstructed as in DRR. You take the X-ray images, and then they are used to align them. Okay, if the set of DRRs are created with a coordinate that is different from your treatment beam, then they are not correct for that treatment. So anytime you check it, you make sure the treatment coordinates of the treatment field and the imaging field, they are same. Nowadays, the treatment planning systems have automatized them. You want to create a set of DRR, they take the coordinates from the treatment field, and so that you don't have to enter by hand. Anytime anything entered manually is very prone to mistake. Okay, so the people have learned from their mistakes and asked the treatment planning system to help them, and that's what they are doing.
That is also the way to identify the patient images.
Say it again.
With matching the DRR.
Mm.
That is the way to also first step to say that these are the correct patient images.
Correct patient images. Yeah.
This is the way we do it. So the first step that you mentioned, patient images are correct.
Yeah.
Identified.
Yeah.
We do it through the DRR.
DRR is just for localizing that where the isocenter is inside the patient. Okay, but if you want to check the anatomy, the target may not be always visible in a planar radiograph. Okay, like a prostate you cannot see in a planar radiograph. So you have to take volumetric images. So that's why cone beam is very helpful. Okay, the planar radiographs, you can see some targets in the lung, because in the lung is a very low density object, and targets are always some high density objects. So in the lung you will see the target volume very well, but those which require some soft tissue contrast, you will not be able to see in planar radiograph. For them, you need either you put a fiducial or you take a volumetric imaging. Okay, so those of you know how the prostate patients are treated nowadays. Usually for prostates, they put some fiducials. In surgically, they put some carbon-based fiducials. Previously, they used to put gold fiducials, but gold is a hygiene material. When you take the image of gold, it will create artifact. So now they have moved to a carbon-based fiducials, which are visible in X-ray images. If those fiducials will be visible in planar radiographs, and when you have a digital reconstructed radiograph, that fiducials are also visible there, and in your X-ray they will be visible. So then you superimpose them and adjust the patient position so that the fiducials in the DRR and the fiducial in the X-ray image are matching. Okay, if if the fiducials are not there, then you have to do either cone beam CT or take a CT on rail image to align those patients based on the target. But bony landmarks, they are always seen in planar radiographs. So mostly when you are using only planar radiographs for patient setup, you use bony landmark. If you want to use soft tissue target for alignment, what do you use? You use cone beam CT or CT on rail. Okay? All right. Okay. Block type 3D dose distribution, multiple planes are consistent with the plan objective. Dose volume histogram consistent with the plan objective. And the OARs meeting the dose tolerance. Parameters for set of fields are correct. Plan is accurately transferred to record and verify system. After the plan check, you check the plan and everything. Then you go to the record and verify system. What is record and verify system? Record and verify system is used to control the treatment for every patient. So before a patient is brought to treatment, after the plan is approved, all those parameters are electronically transferred to the record and verify system. And then all the information that you need to treat the patient is available. So a physicist goes through this, looks at that all the informations are correctly transferred. I put my record and verify systems here. I put my treatment planning system here. Look at one and other. and make sure that all the parameters are correctly transferred. Specifically, we are using many spots. So you have to make sure that the spots that are used for treatment are correct. Similarly, the analogy is for intensity modulated X-ray therapy or VMAT, what is used for control the intensity? The multi-leaf pattern, the segments. So you have to look at the multi-leaf segments, not all of them. Some of them, making sure the number of segments are correct, their shape is correct, and they are properly transferred. One radiation incident happened that when the transfer was taking place from the treatment planning system to the record and verify system or electronic medical system which controls the treatment delivery, the system crashed. Okay, the transfer, during the transfer, the system crashed. One of them just crashed. So then when it's rebooted and nobody checked if the transfer is complete or not for some reason. So at that time, the MUs, monitor units for the total composite field, individual field, and all other parameters were transferred. And for some reason, those fields were not QA'd. That's not a part of their QA program. So during the delivery, the patient was delivered a dose without these segments. So what happened? You deliver a patient a large MU with a very broad open field. So eventually patient died. Okay. So that's why it made a big news in the New York Times. Okay. So we tell our team, you don't want to be in the headline of New York Times. Okay. So make sure that all the things are checked. So that's the reason we have not given up our measurement. All treatment fields are measured so that at least the number of spots, the spot pattern, the log file, all those things are checked. I'll show you a QA report in the afternoon tutorial session, how it looks and what we do, okay? So to make sure that patient treatment fields are correctly delivered. Okay, you have had enough. Now let's summarize. Effective proton therapy QA program is essential. I am not expecting you know all the things I showed you, but this is what is essential. The QA program is essential, and that is 100% responsibility of the physicist. Okay, making sure that QA program is functional and is effective. Okay, it needs innovative ideas to make the QA program efficient and effective. Okay, that is where your intelligence plays the role. Okay, you not only yours, your teams. And automatic plan check, chart check tasks will help. You know, anytime humans do repetitive tasks, there's a possibility of making more mistake. So all those repetitive tasks can be automized. I have a book in myself, Automate the Boring Stuffs by Python. So Python programming has become very useful tool to do this automation and all kinds of things. So you should be good at Python programming so that you can write your own programs to check yourself, okay, to reduce your work, the repetitive work for you. Question remains, how much QA is enough? That is always a big question for everybody. Are you doing too much? Are you doing too less? But that you have to decide that. That's why the recommendations from the other the professional organization help you, just making sure that at least you are doing the minimum QA required, recommended by them. The new QA philosophy is failure mode analysis based QA program. So in industry, they have something called a failure mode analysis, where things can fail and how frequently it will fail. What is the severity of what is the consequence of how severe the consequence. So all those things can be taken account from your experience, and then you can modify your QA program, okay? So this is the reference for comprehensive QA for proton beams and ICRU 78, and there are many other documents available. You put QA for program therapy in Google, and you will get plenty of references. Okay, I don't have to give you those references. Now, Chat GPT is providing all those information. Okay, you even don't need me to come here and give a lecture. Okay, that's it. So I'll stop lecturing now. You can take a break. What is there? This is our proton therapy center, okay? If you want to see the picture. Just take a break. We'll do some, I will meet at, it's already 11:30. We'll meet at 12.
Sir, now you're talking about advances only, no?
Hmm?
About genetics, everything.
Good.
Now you're talking about
Now I'm talking about radiation safety, and then we'll talk about it.
today.
Yeah, everything is hopefully I will finish before launch. If there is something left, we'll do it. You are leaving now?
1 o'clock I'm planning to leave.
Okay, no problem. Yeah, no problem. I'll try to.
This you told now, what are your future things?
Yeah, okay, let's do that fast.
Yes.
Let's do that fast. And then we will do radiation safety. Okay, because radiation safety is the only interesting part.
Yes.
Yeah, okay.
Triple IT. The session there.
Okay, I will finish that part fast because of you. Okay. Where will these talks be loaded to? There's a website where it will be loaded, or
YouTube.
YouTube? The whole world will see it. Oh God, I'm in big trouble. Is there a way I can block it? I should have more.
It's actually live.
Huh?
Live actually.
Yeah, it's live. Oh, God. Children, they'll look at it, say that this is such a how could you do that such a bad job? Or that's what I am. In the history, there are Ravanas, there are all kinds of things. So it's part of our play. Okay, so it's live. Okay, you're not started. Yeah, let me load my things. Okay. Can we not record this part? Is it possible? Can we not record? Not record because.